Okay, so the next chapter in the Alkyne textbook is all about ketones and aldehydes, and I wanted to start off by talking about nomenclature. That is how we name these compounds. And the nomenclature is covered pretty extensively in your textbook, but I wanted to go over just the basics. And just like with any organic molecule, the first thing you always want to do is you want to identify the longest carbon backbone containing your functional group. In this case, the functional group that I'm referring to in the molecule is going to be this aldehyde, and the longest carbon backbone that contains that aldehyde would be 1, 2, 3, 4, 5, 6. So it's going to be 6 carbons long, which means that the parent is going to be hex, indicating 6 carbons, and it's an alkane, so we do AN. And then to indicate that it's an aldehyde, we'd want to change the suffix to AL. So this AL prefix is what is used anytime we're dealing with aldehydes. All right, so it's pretty straightforward. Let's try another example really quick. And in this example, we're going to have a more complicated molecule. And in particular, we're going to have a bromine right here. All right, so when I look at this, the longest carbon chain containing my most important functional group would be 5 carbons long. And in this case, the most important functional group we're dealing with is the aldehyde. We'll talk more about IUPAC priorities here in a second, but the bromine is going to be of lower priority than the aldehyde. Okay, and then over here, I could say really quickly, hey, we've got a stereocenter, and when we're assigning stereochemistry, this would be priority 1, this would be priority 2, this would be priority 3. So we go around clockwise, which indicates that this must be an R stereocenter. So let me quickly erase all of this, and I'll just go ahead and say we've got an R stereocenter. And then over here, we've got a methyl group. And over here, we've got a bromo group, each of which are acting as a substituent. So when we go ahead and we name this, we want to start out with our stereocenter. In this case, there's only 1, so we don't need to number it, but we could say 3R if we really wanted to. And then we want to arrange things in alphabetical order. The bromine, having the B in it, is going to be before the M in methyl, so it'd be R, 3-bromo, to indicate that the bromine is coming off the 3 position, 4-methyl. We've got our substituents taken care of. Now we go to our parent, and it's going to be a pentane, but we need to change the suffix to AL to indicate that this, in fact, is an aldehyde that we're referring to. All right, so let's really quickly jump into ketones, and ketones are going to be a little bit different. Let's even specify up here that we were referring to nomenclature of aldehydes. And then down below, we'll do nomenclature of ketones. All right, and the nomenclature is going to be a little bit different this time. We're going to have a different suffix, but the same idea applies. In this case, we need to identify our longest carbon backbone containing our ketone. And we have a choice. Do we want a number going left to right or right to left? In this case, I would argue that going from right to left is going to be the best approach because that minimizes the numbering, right? If we went the other direction and we look at where this double bond position is, you can see that it would be at position 4 rather than position 3. So that's really not going to be the preferred numbering system. So I'll go ahead and erase all of that. And it's pretty straightforward, but we need to indicate the position of the CO double bond first. So this would be 3 to indicate that the double bond is coming off the 3 position, specifically the CO carbonyl. And then I would say the backbone is 6 carbons long, so it would be 3-hexane, and then -one would be the suffix. So really what this means is that we have a ketone at carbon 3. So that indicates where the CO double bond is going to be. With an aldehyde, we don't have to worry about that numbering because an aldehyde is always going to be at position 1 in this situation, or in this case. So we don't need to worry about indicating that it's presumed to be at number 1. All right, so let's take a look at some special aldehydes. These are IUPAC allowed, even though they don't follow the systematic naming convention that I just went over. All right, so the first one is the most basic of all aldehydes, where you have 2 hydrogens. This is called formaldehyde. This used to be used to embalm bodies or animals. It's not used at a very high concentration anymore because it's known to cause cancer. The next one might be familiar from a previous chapter. If it's attached to an aromatic ring, this is called Benzaldehyde. And then the next one's going to be a little bit different. Oftentimes I hear students call this ethanal, but most people wouldn't call it that. Instead, they call this acetaldehyde. Because this whole group is referred to as an aceto group. So it takes that prefix and uses it to convert it to its aldehyde. All right, and one more. If you've got a cyclohexane ring, this would be cyclohexane carbaldehyde. Let me zoom out a little bit, and there we go. All right, so let's take a look at some special ketones. Again, these are IUPAC allowed. However, they don't follow the naming convention that we just went over up above. And the first one should be pretty familiar to you. You use it in lab to clean a lot. And this is going to be acetone. So ACETONE. And again, it has this aceto prefix because it's got this group on one side over here. So you may notice that prefix getting used a lot in biochemistry and chemistry. The other one that's pretty common is this one, which is acetophenone. And again, you can tell it's got this prefix because it's got this methyl ketone group coming off of one side. And then the last one that's pretty common, in fact, some of you had this as an unknown for one of your labs last term, is this compound where you have 2 aromatic rings, meaning 2 phenyl rings in this case, coming off each side of the ketone. And this is called benzophenone. Pretty common starting material in organic synthesis. All right, so here's a brief introduction. However, like I said, things get a little bit tricky if we have more complicated molecules. So let's take a look at IUPAC priorities if we have more than one functional group. I really liked this list. This list was pulled directly from masterorganicchemistry.com, so I'd encourage you to check out his website. He's got a bunch of really quick tutorials for how to name. But he's kind of oriented things from least important on the bottom to most important up top. So the most important functional groups are at the top of this list. Things like the carbonyl groups tend to be quite important, where things like halogens and nitro groups tend to be really unimportant. That means that if we have something like an alkyne, we use the YNE, but if it's treated as a substituent, not the most important group, we have to change the naming system. So I'll kind of show you how this works using an example. All right, and the example I want to use looks like this. We've got a ketone. We've got an alcohol group coming off of it. Again, I would number my longest carbon chain. It's 5 carbons and it's cyclic. So it'd be a cyclopentane as our parent carbon system. And then over here, off of carbon 2, we've got a stereocenter, and this will be an S stereocenter. And in this case, we've got two different functional groups we need to be concerned with. We've got this ketone functional group, and we've got an alcohol functional group. So the question is, which one's more important? I kind of gave it away. The ketone's more important, which is why I gave it position 1, but let's go check in this list. In fact, I'm going to change the colors here. Okay, so let's go see where the alcohol and ketone are. So the alcohol is right there, and then the ketone is right here. So ketones are more important than alcohols, so that means we are going to go with the suffix ONE, which means we don't want to use that OL suffix for the alcohol. Instead, what we're going to do is we're going to treat that alcohol as a hydroxy substituent. So let's go ahead and name this. So we've got S as our stereocenter, 2-hydroxy. That's what we're going to name that alcohol. Whoops, it should be hydroxy. And then it'd be cyclopentanone. So in this case, this whole group is treated as a substituent. So it's treated as a less important substituent. All right, so in general, I'm not going to purposely try to mix you up in this class. We're going to go with relatively simple naming, but I did want to show you this list because not all functional groups are created equal. Some are more important than others in the eyes of the IUPAC naming system. All right, before we finish up in this video, I just really quickly wanted to go into the preparation of aldehydes. And all of this is going to be review, or at least hopefully it's review. The first way we can make an aldehyde is from a primary alcohol. And you might remember this reaction from last term, but we can convert a primary alcohol to an aldehyde really easily by using a gentle oxidizer like PCC. We don't want to use a strong oxidizer like chromic acid, otherwise we'll overshoot and go to the carboxylic acid. So we have to use a gentle oxidizer to stop at the aldehyde. Another method that we have would be to take something like an alkyne and treat it with ozone, followed by DMS or some sort of reducing agent. And we can make two equivalents of our aldehyde. And if you remember, I told you these basically act like little scissors, and we'll cut those and insert two oxygens. And we also have to remember that those hydrogens are right there. So this should also be review. So we can make it from alkenes. We can also make ketones directly from alkynes. This is one we haven't seen too often. But let's see if we can remember what reagents we need. In this case, we've got this red carbon and green carbon. They're going to stay put. So I've got a red carbon here, and I've got a green carbon here. And as you can see, we're adding a CO double bond to the less substituted side. So it's going to be anti-Markovnikov. And in order to do that, we need 9 BBN, or one of our bulky borane reagents, followed by hydrogen peroxide and sodium hydroxide. So that one's pretty straightforward as well. This really only works if it's a terminal alkyne. And a terminal alkyne basically just means it has to have this proton dangling off the end because we need to have that proton in order to create an aldehyde. All right, so most of this is review from second quarter organic chemistry. But let's quickly jump into a review of ketones as well. All right, with ketones, we saw ketones being created a lot last term. Most of this is going to be similar to the review we just saw for aldehydes, but we can make them from secondary alcohols, where we can oxidize that CO double bond into, or oxidize the CO single bond into a CO double bond. And really you have some options here. You can use PCC because there's no risk of overshooting, or you can use chromic acid, which is made a variety of different ways. You can make it using sodium dichromate, sulfuric acid, and water. That's one of the more common ways. Or you can treat sodium trichromate with acetone and sulfuric acid. Doesn't really matter. Either of these methods will work. We can also make this from alkenes, kind of like what we saw with the aldehyde example. But in this case, your alkene needs to have no hydrogens on it, otherwise you'll get at least one equivalent of an aldehyde. And just like we saw before, you need ozone followed by dimethyl sulfide, or zinc and water, doesn't really matter. And you're going to get two equivalents of your ketone. All right, along the same lines, we can convert an alkyne into a ketone. And I like to color code everything, so I'm going to color code my red carbon and my green carbon so I don't lose track of them. And in this case, you can see it's Markovnikov addition. So we just use sulfuric acid and water, but we need a catalyst, which is usually mercury 2 salt, like HgSO4, and that would give us our Markovnikov addition. There's one last one that we saw last term. Oops. And that's where we can go from benzene to something like acetophenone. And in order to do this, we do our Friedel-Crafts acylation reaction. And again, we need aluminum trichloride, and then we need this acid halide. All right, so hopefully all of this was review for you. If not, just make sure you go back through the sections in your textbook and brush up on these reactions we covered last term. All right, good luck studying, and make sure to complete the quiz on Canvas.